So hi everyone, today I'm going to tell you about some integration work that we have done to experiment with NFS and create bundles for you to be able to take advantage of easily and quickly. The NFS, although it's simple, getting the best performance out of the equipment and the configuration is always a challenge, so you really need to do a lot of work if you want to really optimize the configuration. So that's what we aim to do in this study and would like to share the results and the outcome with you. So we're going to start talking about when NFS is needed and which environments these configurations are targeted towards. And then we're going to talk about how we approached development of this product and how it led to productization of the bundles. And then I'm going to show you some of the performance studies and upcoming work. Basically, we talked about storage in the first 2 days and discussed that all clusters need shared storage. And the requirements of that are dictated by the application and the users. The work that I'm going to talk about today is targeted more towards smaller clusters, small to medium-sized clusters. I know we've been talking a lot about exascale, petascale, but there are not that many petascale systems out there. Most of us still work with smaller configurations, smaller systems, and we deal with challenges in feeding I/O to those systems every day. So this is an attempt to help you do that easier, quicker. The other point is that even for some of the larger clusters, if the code is not very I/O intensive, NFS can still be a good choice. For example, for some of the bioinformatics applications where they are not very I/O intensive, even for larger clusters, 256 nodes and larger clusters, people could use this kind of a configuration. The other point is that many HPC applications are designed in a way that not all the processes do I/O at the same time. For example, a lot of CFD applications use the rank 0 process to do I/O. So depending on how many applications you're running on the cluster at the same time, how many instances you're running at the same time, your I/O patterns on your storage subsystem may not be as high as all the nodes doing I/O at the same time. So here are some of the different subsystems that we need to focus on in designing clusters, and we've been talking about designing balanced configurations, so it's important to make sure we take all the different components into account. From a computation point of view, I think we have good technologies. We know exactly what to do from Intel, AMD. We know how to put scalable clusters together. MPI is getting more and more scalable, so we understand how to take advantage of additional number of nodes. On the interconnect side, we have InfiniBand, we have 10 gigi, so we have access to high-speed interconnects, low-latency interconnects. On the storage side, it's always a challenge to make sure we design the I/O subsystem right way, and this configuration, the NFS configuration that I'm going to talk about today, tries to address that need. So as I mentioned, the goal is to take the guesswork out of building the NFS subsystem. We created configurations ranging from 24 terabytes to 96 terabytes. The performance we are seeing on these configurations range all the way up to 1.4, 1.5 gigabytes per second using IP over IB. In terms of the front-end connectivity, we tried 10 gigabit Ethernet and InfiniBand QDR using IP over IB. And basically, the configuration looks like this. We have a NFS gateway, which is an R710 2U two-socket platform. Within that platform, we have a RAID card attached to MD1200 6 gigabit SAS-based JBODs. Each JBOD can hold up to 12 3.5-inch hard drives. And in order to maximize gigabytes per dollars, we have used the 2 terabyte nearline SAS drives for this configuration. Again, as I mentioned, the goal is to provide a cost-effective solution, cost-effective configuration. We were talking to some of our colleagues yesterday, and they were mentioning the challenges that they have in terms of their budgets. Research budgets are getting smaller and smaller, especially due to the economic crisis. So it's on everybody's mind to build less expensive configurations. So our goal is to provide you that option, but also give you everything, arm you with all the knowledge that you need to properly tune those configurations so that you can get the best out of it. So if you look at some of the components that form the configurations, these are built on Red Hat 5.5 operating system. It uses Red Hat XFS file system on the storage node. We looked at quite a few things to design this the right way. We looked at which RAID mode we should pick, and then we experimented with RAID 5, RAID 6. We looked at RAID 60, and then we looked at LVM. So should we use LVM to aggregate RAID 6s, or should we use the RAID 60 that's in the RAID controller? When we have multiple RAID controllers and when we use LVM, which LVM mode should we use? What is the overhead introduced by LVM? And then we looked at the file system parameters, XFS, how do you tune XFS? We looked at the operating system parameters, how do you tune the OS I/O scheduler, which I/O scheduler algorithm is more appropriate for this kind of workload. And basically documented all these in a white paper that's available on our website. And at the very end of this slide set, you can see that link if you're interested in more details of how we tuned the overall system. So just want to give you a... Was it a question? Okay. Just wanted to give you a quick snapshot of some of the studies that we did that led to the design of these configurations. So one of the things that as I mentioned, that we looked at was the RAID mode. We evaluated RAID 5, RAID 6, RAID 60. And since the MD1200 has 12 hard drives, we looked at 3 ways of partitioning the MD1200s. You could do a RAID 5, basically 2 RAID 5s of 6 drives each in the 12 drive chassis. You could do a RAID 6 of 6 drives or RAID 6 of 12 drives. These were the 3 that we evaluated. In terms of the write bandwidth, we saw that the RAID 6 with 12 drives was giving decent performance. RAID 5 is obviously better than RAID 6 in terms of using the same number of hard drives, but obviously with RAID 5 you have reliability issues. In terms of the read bandwidth, there wasn't much difference between the different RAID modes that we had used. And we looked at reliability. We did an analysis based on 2 terabyte hard drives, 10 to the minus 15 bit error rate. We took the hard drive MTBF and basically halved it to account for the fact that these are going to be used a lot, and build a Markov chain model basically to analyze the reliability of RAID 5 with increasing number of drives. The main parameter that we were looking here was the mean time to data loss. So we wanted to see whether RAID 5 is even feasible for this configuration. And we saw that as you increase the number of drives, the mean time to data loss decreases significantly for the system. As you can see with 84 drives, it comes to about 8 years. So we thought that this is not acceptable, but if you look at RAID 6, that's much higher than the RAID 5. It was about 27,000 years at 84 drives, which is not plotted on this graph. But that's one of the reasons why we chose RAID 6. And if you remember the previous slide, looks like it doesn't give us performance penalty when we configure the RAID 6 with 12 drives. So that was one of the, that was a snapshot of one of the things that we looked at. And we did similar studies for RAID chunk size, how much data we stripe on every disk. We did a similar study for number of NFS daemons, how many NFS daemons we create. We did similar studies for I/O scheduler, so CFQ versus deadline. And after doing all those studies, we implemented all the tuning options that we came up with, and saw that with the tuning options that we have versus just using the default, we see up to a 30% performance difference. So this was quite good, and by implementing these tuning options, you could also enjoy similar benefits. So I'm going to go, okay. So these are the 3 configurations that I mentioned, the 24 terabyte, 48 terabyte, and 96 terabyte, and I have more detailed slides describing each configuration. But this slide just gives you a snapshot of the peak performance that we have observed with each configuration. And you have the 10 gig reads, 10 gig writes, InfiniBand reads, InfiniBand writes. With IP over IB, we were able to see around 1.5, 1.4 gigabytes per second of throughput. With 10 gig, we were pretty close to line rate. We were at 1,200 megabytes per second. Good question. We believe that it's an impact of NFS. The reason is NFS assigns read-ahead cache dependent on number of NFS daemons that you create. For this study, we created 256 NFS daemons, and actually you can see that with increasing number of NFS daemons, your read throughput increases. But there is a balance. Basically, you cannot create too many NFS daemons, then you start hurting your write performance. So it's not necessarily the rate. So if you look at the actual device, if you do the benchmarking on the NFS server directly to the storage, you see different numbers, different characteristics.
And just to clarify, that rating device is not like from your
This is an internal PERC card. So basically, you have the R710 server. In the R710, you have a PERC H100 card with 1 gigabyte cache. And then on the same server, you have 2 hard drives in RAID 1 configuration for the operating system. And we also put additional hard drives in a RAID 0 configuration for your swap space, because if you had to do an XFS file system check rebuild, you may need some swap space. The amount of memory varies depending on the configuration. For smaller configurations, we have 24 gigabytes of memory. For larger configurations, we recommend 48 gigabytes of memory. Again, the RAID mode depends on the configuration. For the smaller configurations, we have RAID 60. And then for the largest configuration, since we have two H800 cards, we create LVM on top of those. This is how the software stack looks like. RHEL 5, update 5, and on top of that, we have the Red Hat XFS. We were using OFED 151 for this particular study. And as you see, no non-standard components, basically all based on standard commodity components. So this is more details about specific configurations. This is the small configuration that we have. So MV1200 with 12 2-terabyte drives, therefore 24 terabytes raw, 20 terabytes usable space. And these were the peak read-write bandwidths that we have seen. I'm going to move over these quickly because we have more detailed performance charts coming up. And this is the 48 terabyte configuration. Basically, you add another MD1200. And the 96 terabyte configuration is we add another RAID card. Basically, you have two H800 cards. You have 4 arrays total. Each group of 2 has RAID 60, and then we aggregate them using LVM. And here are some of the performance study results. This is how our experimental test bed looked like. We had R410s, these are 2-socket 1U platforms, as our clients. They were connected to a QDR IB switch, as well as gigabit Ethernet switch. So in the 10 gig tests, actually clients are using gig, and only the server is using the 10 gig. So here's how the sequential read performance looked like. And as you can see, with increasing number of nodes, there was a point where the performance peaked and then saturated. With the NSS large configuration, we weren't actually getting the saturation point with the total number of clients that we had. You will also notice that since this is the 10 gig study, single client throughput is rather low because each client is actually using single gig. The clients are not equipped with 10 gig cards in this study. On the right, you will see that depending on the number of spindles, we had different performance levels. And actually, we saw that the write performance decreases after a certain point as you increase the number of clients. This is mostly due to disk trashing. Basically, we become disk seek bound as opposed to I/O bound after a certain point, because although each client is doing sequential I/O, when you look from the storage side, since there are so many clients doing sequential I/O, it becomes randomized and you become disk seek bound. And adding more spindles, of course, helps. So if you added more spindles, you would expect to have a straighter graph as opposed to a drop. And these are the nearline SAS drives. So these are not the high RPM SAS drives. If you had same number of spindles, but the 15K SAS drives or the 10K SAS drives, again, you would have a straighter graph. One of the reasons why we picked the 2 terabyte nearline SAS was, as I mentioned, maximizing dollars per gigabyte. So there are different things that you can do to fine-tune those configurations and change the shape of the graphs. But you have to balance basically cost per performance. Looking at the IP over IB, we saw a significant improvement in both read performance and write performance. And here you will see that the single client performance is pretty good. with the large configuration, we get close to 1 gigabytes per second of single client I/O performance with IP over IP. So if your cluster is already equipped with InfiniBand, then this would be a good choice. But if you don't have InfiniBand in your cluster, then you could get the 10 gig version and still enjoy a good, large number of nodes. Still enjoy a good performance level for a large number of nodes.
So that's one thread per node?
This is one thread per node, that's correct. We had 32 nodes. And here are sequential writes. So basically you see the similar type of behavior where it peaks at a certain number of nodes and then starts dropping due to being disk seek bound. We did similar studies with random workloads as well. With random workloads, we were using the 4 kilobyte request size. And the scaling was good. We actually started seeing different configurations differentiating around 24 nodes. We noticed that with InfiniBand versus 10 gig, there wasn't much difference in the random performance because the bottleneck is not the network in this case, but the disks are the bottleneck. So we didn't publish the 10 gig results for the random workloads since they looked very similar to the InfiniBand case. We also did metadata tests with a tool called MD-Test. We created over 1 million files and looked at stat performance, file create performance, file read performance. What I have on the slide is the create performance, but in the full white paper, we discuss all the different metadata operations that I mentioned. So some observations that I already touched upon. With IP over IP, we saw that the single node, single stream I/O performance looks very good. For most node counts, we noticed that IP over IP gives much better performance than 10 gig. But as I mentioned, depending on your workload, if it's a random workload, you may be disk seek bound and, or spindle bound, and you may not see a big difference between 10 gig and InfiniBand. But for sequential workloads, the difference is obvious. And also, as I mentioned, many applications use fewer number of threads than the actual number of processes to do I/O. So if you have, let's say, a 64-node cluster, it doesn't mean that all 64 nodes are going to do I/O at the same time. So you also need to take that into account when looking at the numbers and determining where the peaks and bottoms are. The other point that's important to note is that although you think your workloads are sequential, when the number of nodes increase, the actual workload that's seen on the I/O server may be randomized. So it's always important to do profiling of your application and understand how the I/O workload, how the I/O profile looks on the server, as opposed to thinking, hey, I'm reading just a large file, it's sequential. It may be for a particular application, but when you run multiple instances of different applications on the same cluster, what you see on the I/O server side may be significantly different. I also wanted to give you a snapshot of what's coming up next. So one of the first questions that pops into people's mind is, well, these configurations are good, the sequential I/O numbers look very good, but I have a single NFS server and I'm not very comfortable with that. What's going to happen if my NFS server fails? So for the next version of this white paper, we're doing a study with 2 NFS servers. Of course, you can't use internal RAID cards in this architecture, so we upgraded the
storage enclosure to an MD3200, which is basically what we call an RBOT. It has 2 RAID controllers inside the enclosure, and then you daisy chain MD1200s behind it for expansion. Still using the same 2 terabyte nearline SAS drives, but we have 2 NFS servers, as you see over here, and we're using the Linux HA packages to configure failover. And in this study, we're going to go very deep into details of how you install this, how you configure it, some of the best practices, such as using APC networked power distribution units and using 2 of them, connecting each PDU to a different power supply and a different power bus. So we're going to go talk about those details, how you do fencing of these I/O nodes, these NFS servers, how do you configure the primary fencing device, secondary fencing device, what are the failure modes, what happens when you unplug a network cable, what happens when your when one of your RAID cards go down, so on and so forth. And this is, again, hot off the press, hasn't been presented anywhere or published anywhere yet. We haven't even released the white paper. We should be releasing it in a couple of weeks, so it's exclusive for the HPC Advisory Council. We're seeing very good read throughput on these configurations. In terms of writes, we are slightly below what we see on the non-HA configurations, mostly because we use different tuning options. We use basically sync writes for NFS, and we enable RAID cache mirroring for the writes, so that if there's a failure, we maintain consistency during failover. So in summary, the goal of this study was to do our homework ahead of time and give you what you need to configure your NFS servers the best possible way. It takes, although NFS sounds simple, you create an NFS mount, you export it, and your clients mount it. It takes a lot of work to try different options because there are so many different parameters that you can tune, and picking those options may impact other system parameters such as reliability. So you really need to be careful about how you tune the system, which parameters you pick. I think we spent a lot of time on this, time and energy on this, and basically made all the results available to you so that you can either get similar configurations, deploy it yourself if you're comfortable with it, or depending on which region you're in, we can give you the full configuration installed, configured, associated with the services that go along with it. So hopefully that helps you build your NFS environments for your small, medium-sized clusters. That's basically it. I tried to go a little faster. And here's the link to the white paper. I believe the slides are going to be available. So if you'd like to get more information on the exact commands that we have used to do the study, the exact commands that we have used to do the tuning options, they are listed step by step in that paper. So you can basically take that, follow it, and hopefully reproduce the same results.